Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
To understand why text generation speed eventually hits a hard ceiling, we have to look inside the hardware. Modern AI chips process math incredibly fast, but they are physically restricted by how quickly they can pull data into the processor. Traditional large language models are built on autoregressive architecture. They operate like a typewriter, calculating and predicting text one single token at a time. Every time a model predicts a word, it fetches weights from memory, moves them to the core, calculates, and starts over for the next word. This constant fetching creates a massive traffic jam, hitting memory limits long before maxing out processing power. The result is that highly capable GPU tensor cores sit underutilized. They are forced to wait for data to physically cross the memory bus, completely wasting their computing potential. Google DeepMind released an experimental model called DiffusionGemma, specifically to bypass this physical limitation. To solve this, it completely abandons left-to-right sequential prediction. Instead, it applies a completely new diffusion-based process to decode multiple tokens simultaneously, operating exactly like a massive parallel printing press. By fetching the weights once and computing hundreds of tokens in parallel, DiffusionGemma avoids the memory traffic jam and shifts the operational workload directly onto the GPU's raw processing power. Deploying requires understanding the block architecture, analyzing specific hardware scaling, and mapping the local software stack. Solving the memory bandwidth problem allows consumer hardware to reach text generation speeds up to 4 times faster than standard language models, extracting maximum value from existing hardware limits. To conceptualize this architecture, you have to stop thinking about text generation as writing words on a page and start thinking about it like rendering a two-dimensional image. During a single forward pass, DiffusionGemma generates a complete canvas of exactly 256 tokens. It starts with pure noise and refines that entire 256-cell grid all at once. Every token in the block crystallizes into its final state simultaneously. To generate outputs longer than 256 tokens, the model uses a block autoregressive process. Once a block finishes denoising, it is saved, and a completely fresh block begins rendering next to it. This caching mechanism retains the sequence history, ensuring the new grid perfectly connects to the structural context of the previous one. Processing text as a parallel canvas introduces a massive structural advantage: bidirectional context. Because the whole block exists at the same time, individual tokens can analyze their historical context while simultaneously looking ahead at future context within the exact same pass. As the block refines, the model tracks an internal confidence score for every token. If it detects a specific cell where the data probability drops, it flags an error. The model triggers a dynamic renoising loop, recalculating that weak token using the solid data from the surrounding bidirectional context, correcting the error in real time. Standard language models predict left to right. They cannot look ahead at words they haven't written yet, making this exact real-time, backward and forward self-correction structurally impossible for them. Understanding the parallel logic leads directly to the physical hardware requirements, specifically how much VRAM is needed to hold the model. DiffusionGemma is constructed as a 26 billion parameter architecture. Typically, pushing data through 26 billion parameters simultaneously during local inference incurs severe latency penalties, heavily slowing down generation speeds. To bypass that latency, DeepMind integrated a mixture of experts routing architecture. This ensures that while the total pool contains 26 billion parameters, the model only selectively activates 3.8 billion of them for any specific forward pass. Google partnered directly with NVIDIA to benchmark exactly how this highly efficient routing translates into raw text throughput. This chart displays the resulting tokens per second throughput metrics. Starting at the baseline, a single consumer tier NVIDIA RTX 5090 outputs over 700 tokens per second. Scaling up to enterprise-grade server environments, the NVIDIA H100 GPU pushes that rate beyond 1,000 tokens per second. And when running on a complete NVIDIA DGX station cluster, the throughput climbs to a massive 2,000 tokens per second. These numbers represent single user speed, which operates under completely different physical constraints than systems built to process thousands of simultaneous users. Because the architecture relies on occupying all available tensor cores at once, its performance diminishes significantly in high concurrency cloud environments requiring request batching. By utilizing the entire processor for one request, the model optimizes specifically for instant local responsiveness, rather than distributing its compute power across massive server loads. With the hardware constraints defined, we can map the exact engineering pipeline for executing this model on a local machine. Google released the experimental weights under an open Apache 2.0 license, providing developers direct access to the files. The primary access point for downloading the complete architecture is the Hugging Face repository. The main hurdle when pulling these weights down is physically fitting an uncompressed model of this size into standard consumer VRAM limits. To solve this, developers must apply a 4-bit quantization process to compress the data. Running the 26 billion parameter weights through a 4-bit quantization filter shrinks the footprint to 18 gigabytes. From there, native integrations branch out: VRLM and Hugging Face transformers for NVIDIA, Unsloth for custom pipelines, and MLX for Apple Silicon. Structuring the software stack this way takes a massively complex experimental architecture and successfully deploys it on standard consumer-grade hardware. It is crucial to remember the operational boundaries here. DiffusionGemma is strictly an experimental preview, built to test an architectural theory. Google explicitly notes it is not designed to serve as a direct replacement for foundational production models, like the standard Gemma 4 releases. Its true utility lies in highly specific local interactive workflows, applications built for a single user, where absolute zero-latency responsiveness is a rigid requirement. Because of its bidirectional context, it excels at real-time code infilling and inline document corrections. It strongly outperforms standard models in multi-directional constraints, like complex layout structures or solving grid-based Sudoku. This chart maps specific strengths against weaknesses. On deep scientific reasoning or complex logical deduction, semantic quality drops noticeably. It also struggles heavily in massive cloud server environments, handling high concurrency request patching. But by bypassing sequential autoregressive processing entirely and proving that parallel diffusion can successfully generate discrete tokens, Google has validated a highly efficient, ultra-fast structural pathway for the future of local AI. Since modern language models were introduced, the industry accepted a strict assumption. Machines must generate text left to right, one word at a time, mirroring human speech. This is the autoregressive mechanism. Traditional large language models operate like a mechanical typewriter, calculating the probabilities for a single token, predicting it, and locking it into place before they can even look at the next one. Relying on this sequential process creates a severe architectural limitation. Because the system must wait for one token to finalize before starting the next, its speed cannot scale linearly with newer, faster hardware. Google DeepMind has built a system that abandons sequential generation entirely. It is called DiffusionGemma, an experimental 26 billion parameter open-weight model. Instead of predicting tokens one by one, it applies diffusion-based parallel decoding. It treats text generation like image generation, pulling large, complete blocks of text out of static noise simultaneously. By generating data in parallel, DeepMind achieved up to a 4x speedup over traditional language models running on the exact same hardware. To see exactly how this multiplier is possible, we have to look past the software and examine the physical reality of the microchip, where the true bottleneck of AI generation hides. This GPU schematic shows the core problem: a vast VRAM array, massive tensor cores, and a narrow memory bus. Generating one token requires squeezing the entire weight dictionary across that narrow bus. While data slowly moves, the massive tensor cores sit completely idle. This exact delay is known as the memory bandwidth bottleneck. If you buy faster, more expensive processors for a standard model, you hit diminishing returns almost immediately. The hard speed limit is dictated by the physical width of the memory bus, not the speed of the compute cycles. DiffusionGemma approaches this physical limit by altering the math. Rather than trying to widen the memory bus, the architecture is designed to completely saturate the compute cores with a single data delivery. By shifting the operational burden away from memory transfers and directly onto raw processing power, DiffusionGemma turns text generation from a repetitive data fetching problem into a highly efficient parallel processing engine. To utilize that idle compute power, the model swaps the mechanics of a typewriter for the mechanics of a printing press. DeepMind implemented a framework called block autoregressive diffusion. This diagram shows the model opening a canvas of 256 token slots simultaneously. It fetches the heavy weights across the memory bus just once to evaluate the entire block. With 256 tokens calculated at once, the GPU's tensor cores engage at 100% capacity. For sequences exceeding 256 tokens, the system finishes denoising the first block, saves it to the cache, and seamlessly opens the next canvas to repeat. Achieving localized parallel processing inside a global autoregressive structure yields a massive 4 times throughput multiplier, relying entirely on existing hardware limits. Generating 256 tokens at once collides a secondary and perhaps more vital mechanical advantage: complete structural awareness. In a sequential left-to-right model, a token only sees the words generated before it. It operates under strict unidirectional masking, blind to what comes next. Looking at this central highlighted token in DiffusionGemma, we see bidirectional context. The token has simultaneous visibility into both the past slots and the future slots within its active block. This bidirectional awareness lets the architecture calculate a real-time confidence score for every token. If a score drops mid-generation due to a conflict, the system executes dynamic renoising. It dissolves the problematic token into digital noise and recalculates it based on surrounding context. Traditional sequential models lack this capability entirely. Once a word is printed to the sequence, the model cannot go back and correct it. The parallel canvas acts as a self-correcting drafting environment, providing a structural check on every token as the block is generated. This bidirectional self-correction converts text generation from a rigid chain reaction into an actively malleable fluid state. Pulling back from the abstract mechanics, the strict engineering specifications of DiffusionGemma reveal how this is deployed locally. The model is built on a 26 billion parameter foundation, utilizing a mixture of experts architecture. As this diagram shows, out of 26 billion total parameters, the mixture of experts system selectively filters the processing load, activating only a small subset for any given inference step. The exact active footprint engages only 3.8 billion parameters at once, drastically reducing the required processing weight. This lean activation footprint allows developers to apply 4-bit quantization to the model weights without breaking the system. Fully quantized, the model's operational requirement easily drops below 18 gigabytes of VRAM. Combining the mixture of experts architecture with parallel block diffusion successfully pulls 26 billion parameter performance out of server farms and drops it directly onto consumer-tier GPUs. This bar chart tracks tokens per second output when the model is paired with an optimized NVIDIA stack. We see local inference on an RTX 5090 clearing 700 tokens per second, an H100 surpassing 1,000, and a DGX station scaling to a massive 2,000 tokens per second. However, Google issues an explicit warning with these numbers. DiffusionGemma is an experimental preview. It is not designed to replace foundational production architectures like Gemma 4. This matrix highlights the divide. DiffusionGemma struggles with deep reasoning and falls behind in massive cloud server environments. But it dominates specific edge cases, excelling at local interactive workflows, real-time code infilling, and nonlinear logic constraints like solving Sudoku puzzles. It is a precision tool, highly optimized for instant responsiveness in single-user environments, trading deep analytical reasoning for high-throughput generation. The model weights are currently available to the public on Hugging Face under an open Apache 2.0 license. Out of the box, it features native integration for prominent developer frameworks, including VLLM, Hugging Face Transformers, Unsloth, MLX, and NVIDIA NeMo. DiffusionGemma proves that synthesizing human language does not inherently require a sequential pipeline. It removes the memory bandwidth dependencies that constrain autoregressive models, relying instead on high computational saturation. DiffusionGemma demonstrates that treating language like an image canvas allows generative AI to maximize the throughput potential of existing silicon.